I have a demonstration set up on this air track, and we do it on an air track, so there is a minimum of friction. And we're going to push two cars together, and we hold them together with a spring. The spring is like the explosion, like the dynamite that can push these apart. So here is one car on the air track, then there is a spring, and there's another car. Let this mass be m1 and this mass be m2, and this surface is nearly frictionless. And I hold them together with a string so that I can pull the spring in. So this spring is compressed, and the whole system is at rest. V equals 0. So there is potential energy in that spring. I take a burner, and I burn away this thread. This is the situation before. Momentum before is 0. Total momentum afterwards will also be 0. It's identical to what I did there. And so this object will fly in this direction, and this object will fly in that direction. And you already can tell what the ratio of the velocities will be, because you will see that v2 prime divided by v1 prime, you see it right there, equals m1 divided by m2. And so I will make some predictions about the speed of these two objects. The largest mass, by the way, would get the smallest velocity. And the smallest mass would get the largest velocity, the largest speed. What you see in here are really speeds. We don't have the information on the direction anymore. How do we measure the speed? Well, we actually measure the time for the cars to move 10 centimeters. Each car has a little metal plate which is 10 centimeters long, and it blanks out a light-emitting diode. And the moment that the light-emitting diode is occulted, the timer starts, and the moment that the light-emitting diode emerges again, the timer stops. So that's the way we will measure the time for each car to move by 10 centimeters. The first experiment that I will be doing, M1, is 244 plus or minus 1 gram, and M2 is also 244 plus or minus 1 gram. In other words, the uncertainty in the masses is something like 0.4%. That's just part of life. I can't do much better. The time that it takes for object number 1 to go 10 centimeters is obviously 10 divided by v1, which is the velocity that we want to compare them with. Now, the 10 centimeters is really only known to an accuracy of about 1 millimeters. So that is an uncertainty of 1% in my timing, in my velocity. So this is a 1% uncertainty. So if we measure the times that object number 1 and object number 2 will go through this timing device, a measurement of 10 centimeters, you would expect the times to be the same to within roughly 1 plus 0.5, say 1.5%. There is, however, an additional problem that is very difficult for me to evaluate, and that's the following. If here is that light-emitting diode, and here is that metal plate that I mentioned to you, which comes over this diode, occults the diode, and says, start the timer, and then the other end, of course, moves off, and then the timer stops, that criterion for on and off for one diode may not be exactly the same as for the other. Here is one system, one car will fly in this direction, and here's another system, and the car will fly in that direction. And that's not so easy to evaluate unless you do a lot of experiments. So I would roughly guess, I'm always on the conservative side, that this may add an uncertainty in the criterion of the diode of another millimeters. And so effectively, I really don't know any better than 2 millimeters what the 10 centimeters is. So I would say we really have to allow here for 2% plus 0.4%. So I would predict that the times of these two cars will be the same to within roughly 5%. That would be my prediction.